everyone, it's July the 3rd. Merge nodes between zeros. You're given a head of a linked list which contains a series of integers separated by zeros. The beginning and end of the linked list will have value 0 for every 2 consecutive zeros. Merge all the nodes lying in between into a single node whose value is the sum of all the merged nodes. The modified list should not contain any zeros. Return the head of the modified list. So 4 and 11. 1, 3, 4. Okay, so it doesn't seem to be too hard. Just very procedural, this thing. We're gonna create a node, a head, right? Dummy head. And then what we're gonna do is we will go through this. Right, we start from the 0. If it's 0, we'll reset. Move, add, do this. Add to the result. Reset, yeah. Very standard, I will say. Very standard. Oh, I think it's different, right? Okay. So first of all, we're gonna say list node dummy. Right. And let's call it node. Okay. We're gonna say list node. Rest node. Loop node. Alright. If actually no. So val is not equal to 0. We say sum plus equal to else rest node dot next list node sum sum reset to 0. Okay, something like that. It's like edge case, right? Yeah. Oh, I've done before. Why it took so long last time? Oh, add everything here. Yeah, this looks really weird. I looped this one already. And I just say current. Oh, okay. Yeah, it's the same thing. It's the same thing. 2 pointers, 1 pass. What? No, I'm not doing this way. Unless it tell me to do it this way. This is interesting. Recursion. Each block. Temp equal to head. Sum. Head dot val equal to sum. Head on next. Go next to temp. Okay. Recursions. It's pretty interesting. But no, I'm not doing this way. I like my way. Alright, we have to come back to this. I thought about it a little bit, but no clue. Right, because what we need to do is figure out a way to create a path, any path, but I can't figure out a good way to create a path like really fast. We'll take ON to go through the current path, right? We'll get a path from one node to everybody else, but that's about it. We can get one node to everybody else, but how do we get the node among everybody else? I don't know. Or are you saying we don't need this? I mean, what we want to know is the most frequent, right? I just need to know the most frequent. Like each path basically is just the frequency, right? What we want to know is the frequency. And when two paths, yeah. Let's look at the hints. Okay. Okay. Save the frequency of each edge weight on the path from the root to each node. So, okay, from root to each node, I have a frequency. Then what? Yeah, so each node will have a frequency, right? Each node has a frequency. But from one node to the other, you see, we add those together. If we add those together, then some node will be overrepresented. The frequency of edge weight on the path from A to B is equal to frequency this from A to B minus lowest common ancestor. Yeah, so we need to find the lowest common ancestor. Is there a way to find lowest common ancestor? So the question becomes to find the lowest common ancestor. But how do we find lowest common ancestor? So I have, maybe I can start from, we can do BFS. We start from the target, and then we go out, right? We start from these two, then we go out, and the next level, go out, and see if in this level we have any node that overlaps. If it overlaps, then that is the lowest common ancestor. Is that the right way? Finding lowest common ancestor of two nodes. They have one parent. Okay, from here, we go up, one parent. Yeah, they only have one parent, right? So from this, you have children. So I reverse. I'll find parent. 2 has parent 1, 3 has parent 1, right? So 5 will go to parent 2. 4 will go to parent 2, so that's the lowest common ancestor. But if we want to find, let's say, 6 and 7, so 6, the parent is 3. And 7, the parent is also have 3. But how do I identify it? I identify it by so we can build a path. We build a path for each node from the root down. Right? Wait, how do I find the lowest common ancestor? So basically we have two paths. I think about it as two strings, right? two arrays, then if we go from back to front, we're going to find the first one that's equal. How do we do that? How do we find the first one that's equal? Now I just go one by one, and the first one that exists will be this. Yeah, that actually work, right? So we have a path, then we just go one by one, and the first node that's in the other path. But then we need to check if a node is in the other path, which means a path has to be a set. How a set will work in this case. It cannot be a set. It has to be an array. But if an array, I cannot check. Hold on, let me think again. Yeah, how can I check? Then we have to save like another one. So we have to save the path for each. We have to save the path for each node. We have to turn the path into a set. Right? It's kind of realize what you're doing here. We have to do all that. We have to save the path. We have to save. Now we can save the path as a string. Maybe it'll be easier. No, it has to be an array. And we need to save it also as a set. What's the algorithm for? I don't know. Binary lifting. Binary lifting again. Holy crap. Do you remember binary lifting? Shoot. Binary lifting. I forgot. Lowest common ancestor of a node's UMV lies in the path from U to the root, and then lies from path from V to the root. And if there are multiple nodes, we pick the one that is farthest away from the root node. The desired node W is the lowest ancestor of U of V. In particular, if U is an ancestor of V, then U is the lowest ancestor. For each node, we will pre-compute its ancestor above it, its ancestor 2 nodes above it, its ancestor 4 above it. That is binary lifting. So ij is the 2 to the jth ancestor above the node I. We climb the ancestors of U until we find the highest node, which is not an ancestor of V. X is not an ancestor of V, but up x0 is. We find the highest node, which is not ancestor. We can find this. If up ui is not an ancestor of V, then we can assign u equals this and decrement I. And decrement I. So if an ancestor is not, then I move this up, or decrement I. Why decrement I? Ancestor above, so we are looking at U, and then we say 2 to the ith ancestor. If it's not, then we assign U equals this, so U move up there. And then decrement I. I still don't get it. If up ui is not an ancestor of V, then we can assign U equals this to that ancestor and decrement I. Decrement I. Why decrement I? But we start from the top. L is ceiling log n. is the one, the largest, right? The largest integer that does not go beyond. Ceiling. How do you know up UI is not an ancestor of V? I don't understand. Time in and time out. Yes. Binary lifting. Up vi, so up vi shall equal to up v I minus 1 I minus 1. Holy crap. Okay. Up v0 is the current node and the parent. So current node 0 is that. So if we do 1, I smaller equal, what the hell is L? L is the largest possible. Then UV Okay, T in and T out is used for checking ancestor. This is used to populate this, but I don't understand this one. Oh, because this one's already done. We process the previous one, then we go down, and UPVI minus 1 will be a node we already processed. Okay, how about UPV2? So we'll do UPV1, which we processed. Oh. Okay. Because every node, if I want to know, I set up my 0th level parent. And if I want to know my 1st level parent, then I need to go to my 0th level parent, right? 0th level parent, and also its 0th level parent. And if I want to do UPV2, right? UPV2, then I go up, and then we go up. What are the ones at the top? Root and root. So roots. Wait a second. Roots parent is root. Look at the DFS, right? Root, root. And we have to go L times. But there will be no values. Everybody will be root. We'll just set it to root. Yeah, 1 level is going to be root, 2 levels is going to be root, everybody's going to be root. And then what DFS? Time in, time out. Time in is when we first hit it. Time out is when we done with it. So a node has a time in and has a time out. Okay. So we can compare if it's ancestor by time in. Time in must be earlier, time out must be later. Wow, it's like 2 pieces is very important. One, of course, is the setup of the binary lifting. The other is this is ancestor. So lowest common will be, we go from the top. Yes, we go from the top, and we want to see if it's ancestor. Yes, if it is ancestor. If it is not ancestor. If it is ancestor, we just move down 1, because we have to go, very careful. Right? Very careful. If it is ancestor. Then we go from the top. We check U. Okay, and then we say if it is not ancestor. If it is ancestor, I minus minus. So we immediately cut half. Okay, but if it is not ancestor, then I'll move the U up to that ancestor. Wait, hold a second. So I'm at U up up some level. I want to see if this is ancestor, and then turns out this is not ancestor. So I set my U up. Okay, so from that position, we ask Why it's I minus 1 then? Well, because if it's ancestor, and then this suddenly is not ancestor. So we move up, and we can do I minus minus. Well, we can do that because the current one, if we go up in the same level as before, if they're ancestor, we just keep going down. If they're not ancestor, we'll shoot up again. Because eventually, because I want to get I equal to 0, right? Yeah, if it is ancestor, I just go down, eventually go to 0. Use 0, right? If it is not ancestor, I'll move up. And the goal is also to move it down to 0. Right, the goal is also move it down to 0. So if we can slow move, or we can fast move. Yeah. This part I don't get it. Because it's not ancestor, right? So if I move up, if I move from here, so I have the current, that is not an ancestor, which means ancestrism is higher up, right? That's not an ancestor. So if I go there, how do I know that? Because if previous one is an ancestor, then I cut in half, then it's not an ancestor. Oh yeah, that makes sense, right? So if previous is an ancestor, then I cut in half, and I say if you're cutting in half, then that is not an ancestor. So I move the current to that half position, right? But I don't want to go do it again. So we can just remove one. Ah, now this makes sense. Gosh, binary lifting. Lord. Alright. So yeah, now read through all this. It's very clear. And we have another one called Targent's algorithm. We might want to take a look at this one as well. Binary lifting. Yeah, we read something binary lifting before, but I forgot. What was this one for, binary lifting? Is that kth ancestor? A GB, a rooted tree with n nodes for q queries in the form of kv. We want to find a kth ancestor of v in the tree. This is kth ancestor. Oh, yeah, isn't this the same? This is to find the kth ancestor. And what we want to do now is also kth ancestor. Not exactly kth ancestor. Computing lowest common associated binary lifting. Path aggregates. I think I use path aggregates when to do the union find. Oh, but have to, read this one again. I read this one before, but it's tough. Oh, binary lifting is tough. I am not used to binary lifting. Binary lifting. Alright, that's alright. That's right, we probably need to go read this one more time tomorrow, and I need to read this one more time. Damn. I was guys surprised that we have, I think in this contest have 2 binary lifting. No, I think it's a previous week contest has binary lifting, and this one binary lifting again. Okay, yeah, so this is pretty clear. We'll find the frequency from any root to all the nodes. Yeah, we'll get a frequency. I don't think I'll use a frequency table. I think I will use just a map. No, a counter. Right, a counter. So it'll be a map of counters, right? A map of counters. And the counters will count the frequency of the edges, the weight of the edges. And as we do that, because as we go through this, we can also set up the binary lifting array. And then we do the query. For each query, we will find its lowest common ancestor, right? And then we will have the frequency, the edge wave frequency to this node, and their lowest common ancestor. So the frequency between this node and this node will be the sum of the frequency of these two and minus 2 times the frequency of the path that they overlap, right? And then we have the frequencies. We pick the one with the highest frequency, because that one is the thing that does not change, right? And we need to know the total. So the total minus that highest frequency will be the answer. Okay. All right. I think we're good to go. We're good to go for this, but we have to do this one more time. All right. I'll see you guys tomorrow. Adios.